In this video, I will show you how I automatically calibrate the electrical angle offset without guessing, without trial and error, and without touching the motor. By the end of this video, you will hopefully understand how the calibration works and you will know how to implement it yourself. The idea behind this calibration is simple. I rotate the motor one full mechanical revolution forward, then one full revolution backward by commanding a known electrical angle reference. By comparing what I command with what I measure, I can calculate the electrical angle offset automatically. To get the electrical angle used in a FOC, I take the mechanical angle from the encoder, multiply it by the number of pole pairs, and then add the mechanical angle offset. All of this is wrapped in a modular function to ensure that the value stays in between 0 and 2 pi. Before I can do this calibration, two things must already work. First, the motor phases must be connected correctly. Second, I must be able to generate the phase voltages. To generate the phase voltages UA, UB and UC, I use the Clark-Park transformation. This transformation takes an electrical angle θEL, a direct axis voltage UD and a quadrature axis voltage UQ and convert them into three sine wave voltages the motor needs to rotate properly. Driving a motor like this is called open loop field oriented control. In my case, the phase voltages range from -10 to 10 volts. Since the motor driver can only output positive voltages using PWM, I have to map the voltage values to fit one PWM duty cycle. I normalize each voltage by dividing by the supply voltage. Then I convert this value into a percentage by halving it, shifting it upward to make all values positive, and finally multiplying by 100. This means 10 volts equal 100% duty cycle, 0 volt equal 50% duty cycle, and -10 volt equal 0% duty cycle. This way, each sine wave becomes a PWM signal the hardware can actually generate. I wrote a small function doing all of this, which uses UQ, UD and the electrical angle as inputs and outputs the duty cycles for each phase. Now I can test whether the motor phases are connected correctly by checking if the rotor moves in the positive direction when applying positive voltages to it. First, I apply a small positive voltage, in my case 5 volts, to the direct axis. This aligns the rotor with the stator's magnetic field. Then I slowly rotate the magnetic field by increasing the reference electrical angle. The rotor will follow. While doing that, I measure the mechanical incremental rotor angle. If the measured mechanical angle increases, the motor rotates in a positive direction, which means the phases are connected correctly. If it decreases, two motor phases need to be swapped. In my case, the difference is positive, so everything is fine. Quick thanks to PCBWay for providing all the printed parts and PCBs used in this project. If you are building motor controllers, inverter boards or encoder PCBs like the ones shown here, PCBWay is a reliable go-to. They support everything from simple 2-layer boards to advanced multiplayer designs, with fast turnaround times and consistently high quality. I will leave a link in the description if you would like to check them out. If you have any questions so far, write them down in the comments and hopefully we can clear them up. Once everything is confirmed, the actual calibration can begin. I rotate the motor by applying a small UD voltage and a known reference electrical angle, one full mechanical revolution forward and one full mechanical revolution backward. During this motion, I continuously measure the incremental mechanical angle of the rotor. After the motion is finished, I calculate the mechanical angle error by subtracting the measured angle from the reference angle. Calculating the error for both directions gives me a forward error and a backward error. Then I take the average of the forward and backward error, filter it and use it to build a lookup table. This lookup table outputs a correction offset for any angle between 0 and 2 pi. This offset can then be applied to the electrical angle used by the FOC fully automatically. The calibration code basically consists of two main blocks: forward and backward rotation and data processing for building the lookup table. Let's take a look at the final outcome. This is the motor running without offset correction. With the offset applied, the operation becomes noticeably smoother. You can see that the measured angle no longer fluctuates as much. The torque output is also smoother. And that's how I automatically calibrate the electrical angle offset for my field-oriented control. If this video helped you understand the electrical angle calibration better, consider subscribing or leaving a like. Thank you for watching.